back. On September 14th, officials from the White House and NASA discussed the space agency's asteroid redirect mission during a televised event at NASA's Goddard Space Flight Center. On the mission, which is targeted for launch in December 2021, NASA plans to send a robotic spacecraft to an asteroid tens of millions of miles from Earth, capture a multi-ton boulder, and bring it to an orbit near the Moon for future exploration by astronauts on a following mission aboard NASA's Orion spacecraft. During the live discussion, John Holdren, assistant to President Obama, the mission's scientific and technological benefits, how the mission will support NASA's goal of sending humans to Mars in the 2030s, and how it will demonstrate technology relevant to defending Earth from potentially hazardous asteroids. NASA astronaut and Expedition 47 Commander Tim Kopra made several appearances in the Washington area the week of September 12 to share highlights of his recent 6-month mission aboard the International Space Station. On September 15th, during a Safety and Health Day at NASA headquarters, Kopra spoke with employees about the importance of both to NASA missions and life in general. While on the space station, Kopra's crew conducted human research that could potentially be used to treat patients suffering from ocular diseases such as glaucoma, as well as help NASA prepare humans for health-related issues associated with long-duration spaceflight. Later that afternoon, Kopra showed imagery from his mission at George Mason University during a presentation hosted by the university's Department of Physics and Astronomy. After the program, he answered questions about working at NASA and the future of space exploration. According to a monthly analysis of global temperatures by scientists at NASA's Goddard Institute for Space Studies in New York, August 2016 was not only the warmest August in 136 years of modern record-keeping, but also tied July 2016 for the warmest month ever recorded. August 2016's temperature was 0.16 degrees Celsius warmer than the previous warmest August in 2014. August 2016's record warmth continued a streak of 11 consecutive months dating back to October 2015 that have set new monthly high temperature records. According to NASA and the NASA-supported National Snow and Ice Data Center at the University of Colorado at Boulder, an analysis of satellite data showed that at 1.6 million square miles, the 2016 Arctic sea ice minimum extent is effectively tied with 2007 for the second lowest annual minimum in the satellite record. Since satellites began monitoring sea ice in 1978, researchers have observed a steep decline in the average extent of Arctic sea ice for every month of the year. The sea ice cover of the Arctic Ocean and surrounding seas helps regulate the planet's temperature, influences the circulation of the atmosphere and ocean, and impacts Arctic communities and ecosystems.
Satellites of the space age were small. Sputnik, for instance, weighed just 184.3 pounds. America's first satellite, Explorer 1, was even smaller, at only about 30 pounds. Over time, satellites grew to accommodate more sensors with greater capabilities, but thanks to miniaturization and new technology capabilities, small is back in vogue. NASA is one of many government agencies, universities, and commercial organizations embracing small satellite designs, from tiny CubeSats to microsatellites. A basic CubeSat has 4-inch sides and weighs just a few pounds. A CubeSat can be put into place a number of different ways. It can be a hitchhiker flying to space on board a rocket whose main purpose is to launch a full-size satellite. Or it can be put into orbit from the International Space Station. Astronauts recently used this technique when they deployed the Miniature X-ray Solar Spectrometer, or MinXS, a CubeSat that studies solar flares. In 2018, NASA plans to launch the CubeSat to study solar particles, or CUSP. It will hitch a ride out of Earth orbit during an uncrewed test flight of NASA's Space Launch System. CUSP could serve as a small space weather buoy. Eric Christian is CUSP's lead scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland.
Right now, with our current fleet of large satellites, it's like we're trying to understand weather for the entire Pacific Ocean with just a handful of weather stations. We need to collect data from more locations.
For certain areas of science, having a larger number of less expensive missions will provide a powerful opportunity to really understand a given environment.
If you had, say, 20 CubeSats in different orbits, you could really start to understand the space environment in 3 dimensions.
NASA scientists are taking this approach of using a constellation of sensors to probe the details of a large area with a number of recently launched and upcoming missions. The Cyclone Global Navigation Satellite System, or CYGNSS, launched in December 2016. CYGNSS uses 8 microsatellites to measure ocean surface winds in and near the eyes of tropical cyclones, typhoons, and hurricanes to learn about their rapid intensification. These microsatellites each weigh about 65 pounds, larger than a CubeSat, but still very small compared to traditional satellite designs. Additionally, the first 4 selections from the In-Space Validation of Earth Science Technologies, or INVEST program, recently began launching. The goal of the INVEST program is to validate new technologies in space prior to use in a science mission. Raven, the first of the INVEST CubeSats, was launched in November 2016 to demonstrate a new way to measure radiation reflected by Earth. The next 3 INVEST missions to launch, HARP, IceCube, and Marata, will demonstrate technologies that may pave the way for future satellites to measure clouds and aerosols suspended in Earth's atmosphere, probe the role of icy clouds in climate change, and collect atmospheric temperature, water vapor, and cloud ice data through remote sensing, respectively. NASA's Science Mission Directorate is looking to develop scientific CubeSats that cut across all NASA science through the SMD CubeSat Initiative program. Andrea Martin, Communications Specialist for NASA's Earth Science Technology Office, believes this is just the beginning.
CubeSats could be flown in formation, known as constellations, with quick revisit times to better capture the dynamic processes of Earth. Multiple CubeSats can also take complementary measurements, unachievable by a single larger mission.
She envisions big things ahead for these little satellites.
The technologies that Cobalt's testing right now will one day enable NASA to send robotic or human spaceflight missions to land on Mars, the Moon, Europa, or other solar system destinations where we want to target landing in very hazardous or precise regions such as canyons, craters, on cracked ice fields, close to geysers, or other geological or scientifically interesting locations. So, of autonomous landing technologies, the project is focused on integrating and testing 2 complementary sensors.
And the way it works, it actually uses its camera to take images as it's coming in to land and compares them to its onboard map. And by doing that, you can actually now determine where you are on the map of where you're trying to land. So that allows you to do a number of things. One, it allows you to actually more precisely determine your actual position coming into landing, and then you can actually do diverts to actually land where you want to land. It also allows you to detect and notice things like hazards and actually divert around those hazards as you come into land.
Laser coming on.
And give the spacecraft essentially a set of eyes, so as it's coming into land, it's actually enabling its processor and its computer to see where it's actually going.
Lasers on. We'll be conducting 2 different flight campaigns within Cobalt. One is open loop and the other is closed loop. The difference being that during open loop, the vehicle is not utilizing Cobalt's navigation for planning its maneuvers. It's instead utilizing GPS. During the closed-loop campaign, the vehicle will actually rely on Cobalt navigation.
Copy that. Okay, moving to the engine start page. Cobalt, this is LC. Go, no, go for flight. Pilot, prime engine. Prime. Okay, team, here we go. Massive off to all, 6-second countdown. 5, 4, 3, 2, 1, ignition.
During our flight testing, we take off at one location and then we target a landing site that's 300 meters away. On takeoff, we ascend up to a 500-meter altitude. During that time, our navigation Doppler LiDAR begins sensing velocity and range within the first 5 meters of altitude. The lander vision system begins performing terrain relative navigation at about 50 to 100 meters altitude. So during the ascent, we're getting initial measurements and starting to generate the Cobalt navigation solution. After we reach the 500-meter altitude, the vehicle reduces the engine throttle, the engine thrust, and starts falling back towards the Earth to build up velocity. Once we hit a 25 meter per second downward velocity, we execute a divert maneuver that targets a specified landing location 300 meters downrange. The vehicle then navigates until about a 20-meter altitude above that landing site, and then executes a vertical descent to touchdown. This is all autonomous on Mastin's GPS-based navigation for open loop, and then during closed loop on Cobalt's navigation.
So NASA's out here at the Mojave Spaceport. We're supporting NASA's flight opportunities by testing different technologies here in the desert that are hopefully landing on another planet one day. So when you have your payload and it's going to go land on Mars, it's really nice to know how it's going to function in that landing environment, propulsive landing specifically, which is something we have not done on another planet yet. So instead of taking the risk of sending something all the way to Mars and not knowing whether it works, we can come out here in the desert. Flight Opportunities provides the payload with the ability to come onto our rockets and do a similar type profile to what they will see when they go to land.
Hey guys, great job,
Hands-on. Competitive. Rewarding. NASA's Human Exploration Rover Challenge can't be described in just one word. And while it has evolved over the past 2 decades, its original premise remains the same. Students design and build human-powered rovers to race on a simulated extraterrestrial obstacle course. The course is not for the faint of heart. Designed to mimic the types of terrain potentially found on the Moon, Mars, or other distant destinations astronauts will soon explore. Each year, hundreds of students from high schools, colleges, and universities around the world, just like you, begin an 8 to 10 month journey. One that will take them through the engineering design process and all the way to the U.S. Space and Rocket Center, the official visitor center for NASA's Marshall Space Flight Center. Teams begin their journey by demonstrating their abilities in computer and mechanical engineering, computer modeling, fabrication, welding, and 3D printing. In addition to modeling and building their rovers, teams must also utilize a host of other skills to showcase their work, including marketing, communications, web and social media design, and even fundraising.
That's because Rover Challenge is more than just a race. It combines several aspects of real-world careers into one exciting experiential design challenge. And after all the design and testing is done, teams pack their bags and rovers and head to the Rocket City to network with NASA scientists and engineers. Challenge represents NASA's commitment to providing opportunities for youth to participate in activities that will prepare them to be the next members of a workforce that will lead our robust space exploration programs. It also allows students to conduct relevant, cost-effective research that mimics the challenges that NASA will face as we journey to Mars and beyond.
The big news is that around a very nearby, cold, small star, we found 7 rocky, Earth-sized planets, all of which could potentially have liquid water.
For me, it's mind-blowing. The first time I saw what the system had in it, I just was like, you gotta be kidding me. And then I looked at the data myself, I'm like, yeah, there they all are. It's just, I would have never predicted this. It's beyond, you know, anything I could have ever dreamt of. We're standing on one of these planets, you'd actually see a lot of them sort of in the sky whipping by in these very short orbital periods. I've been curious about the natural world since I was a very small child growing up along the shores of the Chesapeake Bay, where I very quickly learned to study all the different animals and pick up trash, which led me to study marine science and oceanography in school. And during my studies, I learned that the ocean was in a great deal of trouble from human impacts, from overfishing, from pollution, as well as climate change. And I wanted to do something about that. And for me, doing something meant using science and technology to find novel ways to keep track of what was happening in the ocean and look for solutions. Coral reefs are valued at billions of dollars across the world for fisheries, sustenance fisheries in island nations.
Tourism and new compounds for the pharmaceutical industry are 2 examples of how coral reefs have contributed a lot of money and generated wealth for a lot of people. We have this tremendous wealth of different types of ecosystems and species on this planet, and having these reefs around to maintain a sort of biological stock of genetic uniqueness is really important for genetic diversity, ecosystem health, and resilience of the ecosystem in the face of things like climate change and other sort of stresses they may encounter in the future.
They've been called the canary in the coal mine. They're one of the first marine ecosystems to start to show very significant degradation from ocean temperatures increasing and ocean acidification. And there simply aren't enough people that can be scuba diving in the water all the time to tell you how the coral reefs are doing. So we need new ways to monitor them using things like satellite imagery that can easily cover all parts of the world, even in places that you can't very readily get a person to. What the ER2 is doing is telling us what coral reefs would look like from space.
I'm an environmental scientist. I study ecosystems. I study how those ecosystems are impacted by external pressures such as climate and population. Our part in this project is to understand the color of coral reef signatures coming out of the water. What colors will the Hysperia sensor see? Live corals look very different from dead algae-encrusted corals, and they look very different from the surrounding uncolonized sand and coral rubble. So by looking at the detailed spectrum of light coming out of the water, the visible and near-infrared portion of the spectrum, we believe we'll be able to say something about where the coral resides and how healthy it is. In order to interpret the data that's being collected by the ER2, you have to know something about the inherent reflectance of the features in the ocean floor that we're interested in. Healthy coral, not healthy coral, bare sand, and rubble. So what we're doing is we're measuring in water the reflectance of the ocean floor, very close to the ocean floor. But also we're deploying radiometers at the ocean surface so that we can understand the change in that color as it propagates through the water column to the surface. That's the information that needs to be taken into consideration when we try to interpret the data in terms of coral health. We have to essentially remove the effects of water.
This is something relatively new, using satellite imagery, using hyperspectral imagery to categorize coral reefs. We're collecting bottom spectra, obvious in a satellite image, whether a pixel is coral or algae and how much coral is in it. And to do that really well, we need to collect both pieces of information at the same time. We need an airborne image, and we also need to know exactly what's going on in the water. We can be collecting in-water data to match up with those specific images. And so we know that in a particular pixel, there's a certain amount of coral, a certain amount of algae. It better informs us how, in the future, we can remove the atmosphere and the water effects from the satellite data.
Call this coconut one. Is that? We got it inside. Our autonomous kayak system is a fully autonomous platform that's customizable, configurable, and made entirely with off-the-shelf components. It'll be towing an optical sled from the U.S. Naval Research Laboratory, and we'll also have it towing a YSI XO2 water quality parameter monitoring sonde, which gives us the ability to measure chlorophyll A, fluorescent dissolved organic matter, pH, temperature, and salinity.
These sensors are providing
Earth, a world dominated by water. Trillions of gallons flow freely across the surface of our blue-green planet. While we once thought oceans made our planet unique, we're now coming to realize that ocean worlds are all around us. Our planet retains its atmosphere and, in turn, its abundance of liquid water, thanks in part to a very strong magnetic field, which provides protection from the solar wind. Without this magnetic field, our atmosphere would be stripped away, leaving the pale blue dot looking more like one of our neighbors. Scientists believe Venus's early oceans evaporated. With no water left on the surface, carbon dioxide built up in the atmosphere, leading to a runaway greenhouse effect that created present conditions. Likewise, Mars appears to have had oceans long ago, but the red planet's global magnetic field decayed, leaving it vulnerable to atmospheric erosion by the solar wind. Farther from the sun, in the sub-freezing temperatures of the outer solar system, it may seem impossible for liquid water to exist. However, not only does it exist, but in some places, it may be more abundant than on Earth. Jupiter is orbited by at least 3 moons that contain oceans: Europa, Ganymede, and Callisto. Europa is crisscrossed by cracks and semi-rectangular features that look like ice rafts frozen into the surface. Below those immobile icebergs, researchers believe there is a vast ocean just below the icy crust, warmed by the tidal forces of Jupiter, containing about twice as much water as is found on Earth. In 2014 and 2016, The Hubble Space Telescope has observed what appear to be water vapor plumes coming out of the cracks near the South Pole. Photos of Ganymede from the Galileo space probe show Callisto also seems to contain a saltwater ocean beneath the icy crust, betraying its presence by the effects of Callisto on Jupiter's overlying magnetic field. In 2005, NASA's Cassini spacecraft found Saturn's moon Enceladus busily puffing plumes of water vapor and organic compounds out through fissures now known as tiger stripes in its frozen carapace. Cassini flew through the plumes frequently since then, and has discovered nanosilica grains and the presence of molecular hydrogen, both suggesting the movement of heated water on the seafloor of the icy moon. Other evidence provided by Cassini has convinced researchers that Enceladus' surface is a mixture mostly of methane with smaller amounts of ethane and other hard-to-freeze hydrocarbons. Other bodies around the solar system also show signs of liquid water. In 2014, scientists using the European Space Agency-led Herschel Space Observatory detected water vapor coming from two regions of the dwarf planet Ceres. NASA's Dawn probe reached Ceres in 2015, and while the water vapor had subsided, there were other signs of water. Ahuna Mons is an ice mountain apparently formed from repeated eruptions of salty, muddy water. Also, widely reported bright spots in Ceres' crater Akator are thought to be deposits of salt left behind by the escape and sublimation of briny water from below. Even distant Pluto may be an ocean world. As revealed by the recent flyby of New Horizons, Pluto's strangely molded surface features suggest the presence of a liquid underground. As astronomers look beyond our solar system, they are finding exoplanets of sizes and distances from their stars that could have oceans. And based on our solar system, these exoplanets could potentially have moons with oceans as well. The locations of water within the diverse environments of our own planetary system will guide and inform the search for oceans beyond our solar system. Next time you look out over the ocean, think about our neighboring worlds. They may have more in common with our own ocean world than we once believed was possible.
Head to the backyard with your telescope at dusk for a rare evening with planet Jupiter. In fact, you can spend all night long with the gas giant. It will be at opposition, opposite the sun in the sky, with the Earth in between. Jupiter will be especially dazzling. This is its closest approach to Earth in 2017, making it appear at its largest and brightest. And since it only happens every 13 months, you'll have a long wait for your next big date. But on this occasion, as the sun dips below the western horizon, you and Jupiter will just be getting started. The planet will be rising in the east. By midnight, Jupiter will be beaming overhead, outshining most of its competition in the night sky. It will be well placed near Spica, the brightest star in the constellation Virgo, but will easily upstage even this heavenly body. Aim your scope at the life of the party. The view will take your breath away. With Jupiter so close, the view through even an inexpensive telescope will be great, says Brian Day of NASA's Solar System Exploration Research Virtual Institute. You'll see the planet's cloud bands and storm systems, and you can even watch its four largest moons, called the Galilean moons, change position as they orbit. Io, Europa, Ganymede, and Callisto will appear as bright pinpricks of light, with their positions moving noticeably near Jupiter throughout the night. While these moons look calm from a distance, they are actually very active. Io, Jupiter's innermost moon, is the most volcanically active body in the solar system. There are oceans of liquid water seething beneath the crusts of ice, encasing Europa, Ganymede, and Callisto. Right now, NASA's Juno spacecraft is orbiting Jupiter too. Since summer 2016, it has been returning incredible images with never-before-seen resolution of Jupiter's atmosphere. With the previous Jupiter mission, Galileo, ending in 2003, many years passed between these two missions, and much happened in our continuous exploration of the solar system. During the years between the Galileo and Juno missions, we depended on telescopes such as Hubble as well as amateur observations, notes Day. And the amateur astronomer community really stepped up. They're constantly monitoring Jupiter's atmosphere and have even reported new storm systems on the planet. Some of the images they have taken are pretty amazing. You'd swear they were taken from orbit. Amateur astronomer Damian Peach has the opposition highlighted on his calendar. He says, "My own imaging plans are already underway for this apparition using primarily a 1-meter telescope located near Las Campanas Observatory in Chile. If it's cloudy on the night of April 7th, don't despair. Jupiter will still be close over the following weeks, only about 3% farther away a month after opposition. As Jupiter appears higher in the sky each evening and the nights grow warmer, this spring should be a great time to keep watching the giant planet. An all-nighter with Jupiter will be a great opportunity to hone your own."
"40 light-years from Earth, a rocky world named 55 Cancri E circles perilously close to a stellar inferno. Completing one orbit in only 18 hours, the alien planet is 26 times closer to its parent star than Mercury is to the Sun. If Earth were in the same position, the soil beneath our feet would heat up to about 3,200 degrees Fahrenheit. Researchers have long thought that 55 Cancri E must be a wasteland of parched rock. Now they're thinking again. New observations by NASA's Spitzer Space Telescope suggest that 55 Cancri E may be wetter and weirder than anyone imagined. Spitzer recently measured the extraordinarily small amount of light 55 Cancri E blocks when it crosses in front of its star. These transits occur every 18 hours, giving researchers repeated opportunities to gather the data they need to estimate the width, volume, and density of the planet. According to the new observations, 55 Cancri E has a mass 7.8 times and a radius just over twice that of Earth. Those properties place 55 Cancri E in the super-Earth class of exoplanets, a few dozen of which have been found. Only a handful of known super-Earths, however, cross the face of their stars as viewed from our vantage point in the cosmos, so 55 Cancri E is better understood than most. When 55 Cancri E was discovered in 2004, initial estimates of its size and mass were consistent with a dense planet of solid rock. Spitzer data suggests otherwise. About a fifth of the planet's mass must be made of light elements and compounds, including water. Given the intense heat and high pressure these materials likely experience, researchers think the compounds likely exist in a supercritical fluid state. A supercritical fluid is a high-pressure, high-temperature state of matter best described as a liquid-like gas and a marvelous solvent. Water becomes supercritical in some steam turbines, and it tends to dissolve the tips of the turbine blades. Supercritical carbon dioxide is used to remove caffeine from coffee beans, and sometimes to dry clean clothes. Liquid-fueled rocket propellant is also supercritical when it emerges from the tail of a spaceship. On 55 Cancri E, this stuff may be literally oozing, or is it steaming, out of the rocks. With supercritical solvents rising from the planet's surface, a star of terrifying proportions filling much of the daytime sky, and whole years rushing by in a matter of hours, 55 Cancri E teaches a valuable lesson. Just because a planet is similar in size to Earth does not mean the planet is like Earth. It's something
The universe is a big place, and there are a lot of things out there that astronomers can't identify. NASA's Fermi Space Telescope has just found about 600 examples. The Fermi team recently released the second catalog of gamma-ray sources detected by their satellite's Large Area Telescope. Of the 1,873 sources found, nearly one-third are complete mysteries. No one knows what they are. Fermi sees gamma rays coming from directions in the sky where there are no obvious objects likely to produce this kind of radiation, says David Thompson, Fermi's deputy project scientist. It's a puzzle. Gamma rays are by their very nature heralds of great energy and violence. They are a super-energetic form of light produced by sources such as black holes and massive exploding stars. Gamma rays are so energetic that ordinary lenses and mirrors do not work. As a result, gamma-ray telescopes can't always get a sharp enough focus to determine exactly where the sources are. And therein lies the mystery. For 2/3 of the new catalog sources, the Fermi scientists can, with at least reasonable certainty, locate a known gamma-ray producing object, such as a pulsar or blazar. But the remaining third, the mystery sources, have the researchers stumped, at least for now, and they are the most tantalizing. Some of the mystery sources could be clouds of dark matter, something that's never been seen before. About 85% of the gravitational mass of the universe is dark matter. The stuff we see makes up the rest. Dark matter is something that pulls on things with the force of its gravity, but can't be detected in any other way. It doesn't shine, doesn't emit or scatter light, hence the name dark matter. Astronomers are not able to detect dark matter directly using optical or radio telescopes, but dark matter just might shine in gamma rays. We've been using Fermi to search for dark matter for a long time, says the principal investigator for the Large Area Telescope, Peter Michelson, of Stanford University. Some researchers believe that when two dark matter antiparticles bump into each other, they will annihilate, producing gamma rays. Concentrated clouds of dark matter could form a gamma-ray source at specific wavelengths detectable by Fermi. If we see a bump in the gamma-ray spectrum, a narrow spectral line at high energies corresponding to the energy of the annihilating particles, we could be the first to apprehend dark matter, says Michelson. So far, however, the team doesn't have enough data on the mystery sources to confirm or rule out the dark matter hypothesis. Other possibilities include undiscovered pulsars, supernova remnants, and colliding clusters of galaxies. The scientists plan to continue observing until they have some answers.
The Special Ingredients of Earth, presented by Science at NASA. With its blue skies, puffy white clouds, warm beaches, and abundant life, planet Earth is a pretty special place. A quick survey of the solar system reveals nothing else like it. But how special is Earth really? One way to find out is to look for other worlds like ours elsewhere in the galaxy. Astronomers using NASA's Kepler Space Telescope and other observatories have been doing just that. In recent years, they've been finding other planets increasingly similar to Earth, but still none that appear as hospitable as our home world. For those researchers, the search goes on. Another group of researchers have taken an entirely different approach. Instead of looking for Earth-like planets, they've been looking for Earth-like ingredients. Consider the following. Our planet is rich in elements such as carbon, oxygen, iron, magnesium, silicon, and sulfur, the stuff of rocks, air, oceans, and life. Are these elements widespread elsewhere in the universe? To find out, a team of astronomers led by Aurora Simeonescu, an astrophysicist at the Japan Aerospace Exploration Agency, or JAXA, in Sagamihara, Japan, used Suzaku, a Japanese X-ray satellite with NASA participation, to survey a cluster of galaxies located in the direction of the constellation Virgo. The Virgo cluster is a massive swarm of more than 2,000 galaxies, many similar in appearance to our own Milky Way, located about 54 million light-years away. The space between the member galaxies is filled with a diffuse gas so hot that it glows in X-rays. Instruments on board Suzaku were able to look at that gas and determine which elements it is made of. Reporting their findings in the Astrophysical Journal letters, Simeonescu and her colleagues reported findings of iron, magnesium, silicon, and sulfur throughout the Virgo galaxy cluster. Simeonescu says, the elemental ratios are constant throughout the entire volume of the cluster and roughly consistent with the composition of the Sun and most of the stars in our own galaxy. When the universe was born in the Big Bang 13.8 billion years ago, Elements heavier than carbon were rare. These elements are present today mainly because of supernova explosions. Massive stars cook elements such as carbon, oxygen, iron, magnesium, silicon, and sulfur in their hot cores, and then spew them far and wide when the stars explode. According to the observations of Suzaku, the ingredients for making sun-like stars and Earth-like planets have been scattered far and wide by these explosions. Indeed, they appear to be widespread in the cosmos. The elements so important to life on Earth are available on average in similar relative proportions throughout the bulk of the universe, adds Simeonescu. In other words, the chemical requirements for life are common. Earth is still special, but according to Suzaku, there might be other special places too. Suzaku recently completed its highly successful mission. On February 17, 2016, JAXA launched a follow-up mission to continue the survey. Hitomi, previously named Astro H before launch, is a Japanese-led observatory carrying a key NASA instrument. The observatory will extend such studies to clusters of galaxies far beyond Virgo. For more news from the distant corners of the cosmos, stay tuned to science.nasa.gov.
Не туда остановилась трансляция.